we go. Topic 1.3, rates of change in linear and quadratic functions. So the first thing I want to talk about is a linear function. So we need a good reader. And Eli is going to be our reader here. Here we go.
For any linear function, the average rate of change over any length input value interval is constant.
Is constant, exactly. All right. So the average rate of change, what was that again? Algebra slope. So the algebra slope is constant. It's the same. All right, keep going.
We often think of this as a
slope. This is the slope of the line. So an average rate of change is algebra slope. It is the slope of the line. And that slope is constant when it's a linear function. All right? Because linear has what in it? Line. It has line in it. All right, so let's look at example 1. So this table gives us some values. Explain why this function is not linear. To be linear, the average rate of change must be what? Constant. It's the same. So let's do average rate of change. So let's do our rise over run, basically. So what is my y2 from my interval 1 to 2? 7 minus 4 over 2 minus 1, right? And so what is my slope from the interval 1 to 2? 3. All right, let's do it again. And so now I'm going from 2 to 4. And so now if I have to do my slope of it, or my average rate of change, it would be 10 minus 7 over 4 minus 2. So what do I have on this one? I have 3 halves. So first of all, is my average rate of change constant? No, I can almost stop there, but I'm going to keep going because I'm not a quitter. All right, and so what do we get on this one? We get 13 minus what? 10 over a minus 4. And so what is my slope between those two intervals? 3/4. All right. And so what we should notice here is this is not a linear function, not a linear function, not linear, because why? The rate of change is not constant. That's beautiful. The rate of change is not constant. It's not constant. Awesome. All right, cool. All right, let's look at example 2 now. So we have a quadratic function. I am literally telling you that it's a quadratic function. And so I have the basic quadratic, the basic parent function of g of x is equal to x squared. And so we're going to complete the table of values and then talk about the average rates of change. So here we go. So I'm going to figure out what my g of x, my y value is when I substitute in 3. So Mr. Tompkins, what is it? 9. Very nice. All right, and so then we square -1, we get what? 1. We square 1, we get 1. We square 3, we get 9. And we square 5, and we get 25. Fantastic. So to try to figure out if it's a linear function, it's not linear. It literally told you it's a quadratic, but we're just going to talk about it. We need to find the average rate of changes on them. So we're going to do it just like we did on the last example. So how do we find an average rate of change on the interval -3 to -1? Our y2 minus y1 over x2 minus x1. Exactly. So we'd have 1 minus 9 over minus -3. Beautiful. And so what would that become? Negative. Okay, we can just go straight to -4. I'm liking that. That's good. I like it. All right, and so now let's do it again. And so now we're going to go from -1 to 1. And so what is my change in y? 0 over 2. So we'd end up having what? 0. All right. And so what's my change in y next? Let's keep going. So what's my change in y next? 8 over the change in x, which is how much? 2. And so now we have a slope or an average rate of change of what? 4. This is good. All right. And so now let's keep going. So now if we go to 9 to 25, what's my change in y, or g of x in this case? 16 over how much? 2. And so what do I get there? I get 8. So the average rate of change, or my slope, is 8 there. All right, and so if I were to fill in this little table, I guess we got -4, we got 0, we got 4, we got 8. Now, is this a linear function? No, because my average rate of changes are not constant. However, we should notice something. We should notice a pattern, because math's about patterns. What do we notice about them? They're going up by 4. So the average rate of changes have a change that is constant. That's good. That's a good nugget. All right, and so what's happening here is this is adding 4. This is adding 4. This is adding 4. And so it's not the first rate of change is constant. It's the what? The change of the change is constant. It's the second rate of change is constant, or my second difference is constant. That's what actually makes it a quadratic. So we notice that the rate of change, or the average rate of changes, are linear. The second differences are constant. Three.
Selected values of various functions are given in the tables below. For each table determine if the function can be linear, quadratic, or deviant.
All right, fantastic. So we always have to figure out if they're linear first. So let's try that out first. So to be linear, the average rate of changes are constant. So what's my change in y right here? 1. Over, what's my change in x? 1. So what's my slope? 1. So my average rate of change there is 1. Let's do it again. And so what's my change in y? 3. And so I'd get 3 over 1, which is, you guys are so smart. All right, keep going. Let's do it again. So what's my rate of change? 5 over 1, which is 5. Very nice. So was this a linear function? No, my average rate of changes were not constant, were they? However, I should notice something. What did I notice? They're increasing by 2, aren't they? The average rate of changes are increasing by 2. So, therefore, this is a what kind of function? This is a quadratic. This is a quadratic. I don't know why I went capitalized, but I'm just going with it now. All right, so that's a quadratic. Now, there's 2 reasons why I could list it as the reason why it's a quadratic. So, the second differences are constant, or probably I forgot differences. Second differences are constant, or they'll probably say what? The average rate of changes are linear. All right. The rate of the average rate of changes are constant. All right. Pretty good? Cool. Let's do another one. Let's look at part B. So I need to find the average rate of change first. And so what's my difference of y's? 1 over 1, which is very nice. And then let's do it again. So what's my change in y? 3 over 3. Very nice. And how much is that? 1. Very nice. All right. And then what do we get? 5 over 5, which is 1. So what do we know? What do we know? This is linear. So tell me why. Oh, that's good. That's good. Why is it linear? What? The average rate of changes are constant. Exactly. The average rate of changes are constant. All right, let's keep going. All right, and so let's look at this next one. So what's my change in y? 2 over 2, which is 1. All right, let's keep going. And so what's my change in y? 1 over 2. I can't simplify that one. All right, and then let's keep going. All right, so what's my change in y? 0 over what? 2, which is the same thing as 0. Awesome. So is this a linear function, Mr. Mucci? Huh? No. No. But what happened? Love this, all right? It decreases by 1/2. So this is you have to subtract 1/2 each time, don't we? All right? And so what does this actually make it? A quadratic. I'm not going to write it, but I want you to. So what are the reasons why this is a quadratic? We'll say it just orally for me. What are the reasons? The second differences are constant, or the average rate of changes are linear. The rate of the average rate of change, or the change of the average rate of changes, are constant. All right. All right, so now let's talk about concavity. All right, so we've talked about concavity. We hold water or we spill water, right? All right, and so now we're going to talk about more of the mathematical terms of what's happening with concavity. So I need a beautiful reader. Briggs is going to be my reader. Oh my goodness, yes.
Talking about the average change over an equal length input value intervals is.
All right, so the average change is what? What do you think it is to be concave up? The average change is increasing. Increasing. So the average change is increasing to make it concave up. All right, let's go concave down now.
The average change over equal length input value intervals is.
What do you think? Decreasing. That's what I'm talking about. All right. Now, I kind of want to talk about those examples that we just did. So if you look at part A that we just did, this is a quadratic. Quadratics are like the epitome of concavity. It's like the easiest one that we can do. And so if I have this on part A, that one's going to be concave which way? What do you think it's going to be? If my second differences are positive, which means my average rate of changes are increasing, this is concave what? Up. This one would be concave what? Down, because my average rate of changes are decreasing. My second differences are negative. All right, so that's a great way to think of it. So for concave up, my average rate of changes are increasing. Therefore, my second differences is positive. My second difference is positive. If I have concave down, what do we know about my second differences? They're negative. So it's the same thing. It's just another way to talk about it. And I need you to know all of those ways to talk about it. All right? Words matter. All right, example 4. Briggs, pick a reader, quick.
Example 4. Selected values of the function k, m, and p are given in the table below. For each function, determine if the function could be concave up, concave down, or neither over its domain.
All right, beautiful. All right, so to talk about concavity, we kind of have to get to our what difference? Our second difference. We have to figure out if the rate of change is increasing or decreasing. All right, but we still need rate of change, so we need to do it. Here we go. So what's the difference of my y's? -3. Good. What's the difference of my x's? 0.1. And so what does the average rate of change give me on this one? Dividing by 0.1 is really multiplying by how much? 10. So what do we get? -30. Very nice. And then let's do the next one. So now what's my change in y? -2 over 0.1. So how much is that? -20. Very nice. All right. And then -1 to -2, what we got? -1 over 0.1. So what do we have? -10. So is this a linear function, by the way? No, it's not linear. Okay, because this is moving, isn't it? So what's my second difference? How do I go from -30 to -20? +10. And then -20 to -10? +10. So what do we know about this? Okay, it is a quadratic, true, but let's answer our question. It is a quadratic. Totally agree. Totally agree. However, what is my concavity? It's concave up. Concave up. Why? Why is it concave up? The second difference is positive. Okay, that's one great way to say it. However, that's probably not how they're going to say it. They could. Second difference is positive. Or what? The average rate of change is what? Increasing. There it is. The average rate of change is increasing. All right. Cool. Let's look at part B. All right. So 1 to 4, or 1 to 1.1. So 1 to 4 for my y values. What's my change? 3 over. So what do I got? All right. Let's do it again. So 4 to 7. 3 over. So what do I got? We can almost stop there. Is this going to have concavity? It's not. Okay. okay, because I didn't move anywhere. But I want to finish it up. All right, cool. So what do we get? 3 over, which is 30. What do we know about this function now that I did the last one? It's linear. Does a line have concavity? No, it doesn't hold nor spill water. All right, it doesn't have concavity. And so this is neither. Why? Okay, because it's linear, true. All right, but why? Because the average rate of changes are what? Constant. All right, beautiful. All right, let's look at part C. Let's look at part C. All right, so what's my change? 6 over what? 0.1, which is what? Sissy. All right, and then 7 to 11. How much we got? 4 over 0.1, which is cool. All right, and then what do we got? 2 over 0.1, which is 20. Look how good you guys are doing at average rate of changes now. Gosh, it's like we practice. This is so cool. All right, and so is this linear? Is this linear? No, I don't think so either. Abby, what is it? What's happening with 60, 40, 20? What's happening? Minus 20. It's going down 20, isn't it? It's going down. And so what do you know about the concavity? Concave down. This is concave down. Now tell me why. The average rate of change is decreasing. That is beautiful. That is beautiful. All right. The second difference is negative. The average rate of change is decreasing. There it is. All right.